Okay, chapter 9, this was the chapter on solutions. So we needed to first off categorize what kind of matter is a solution. Well, a solution is a homogeneous mixture, and under the umbrella of homogeneous mixtures, you can either have a solution or a colloid. What is the difference? Okay, it's important for you to know the difference. It all has to do with particle size. Okay, so in a solution, the particle size was less than like 2 nanometers. So mostly you have things like ions in a solution. For a colloid, the particle size was between, I think, 2 nanometers to like 500 nanometers. Okay, so just larger particles in a colloid than in a solution. Parts of a solution. We have 2 parts of a solution. We have the solute. This is the thing dissolved in the solvent. It is present in lesser amount. And we have the solvent. This is the thing that dissolves solute. And it's present in greater amount. Okay? Once we identified what a solution is and the parts of it, we then needed to look at how do we know when we're going to get a solute that is soluble in a particular solvent. And we had this phrase, like dissolves like, which is all pointing to the kind of intermolecular forces between solute and solvent particles. So if solute particles have similar intermolecular forces as solvent, I should say molecules, not particles. Same thing over here. Solute molecules. Then solute will be soluble. Okay, if the solute molecules have similar intermolecular forces as solvent molecules, solute will be soluble. Okay, so polar solutes dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. But nonpolar solutes do not dissolve in polar solvents, okay? So that's where this phrase, like dissolves like. If they're both polar, the solute, solvent, they will be soluble. If they're both nonpolar, they will be soluble. So you need to remember, it's critical that you have a good understanding of how to judge molarity of a molecule, and then the kind of intermolecular forces between molecules. Okay. Let's see. Oh, if you want to practice this, 9.35 is a great practice problem. Also, understanding how temperature can manipulate solubility. So solids become more soluble in a liquid as temperature, keyword, increases. If temperature decreases, solids become less soluble. All right, but as temperature increases, solids become more soluble in a liquid. Gases become less soluble in a liquid as temperature increases. Okay? They become more soluble in a liquid as temperature decreases. All right, and then with all of this, we kind of ended with Henry's law, which says that gas solubility increases as pressure increases. And there is our equation. C1 over P1 equals C2 over P2. Remember, the units for concentration here are grams per 100 milliliters. And then pressure can be anything. It could be ATM, it could be PSI, it could be pascals. Okay, but remember, the units for concentration are gram per 100 ml, and you do not divide by the 100 ml. You treat it as a unit. All right. So knowing how to use Henry's law, there were definitely a lot of homework problems. By the way, you still have access to all your Mastering Chemistry homework. So if you want to go rework any problems from Mastering Chemistry, those are all still available to you. And then Chapter 9 continued. Let's see. This is the last slide, by the way. We had a few equations. So we had, this was for concentration. Determining concentration of a solution, the amount of solute in a given amount of solvent, that is a concentration. So the first equation we had there was a weight volume percent equation, which just says that weight volume percent equals the grams of solute divided by, key here, milliliters of solution. However much solution you have total, just make sure it's in milliliters, and then times 100, okay, because we want to turn it to 1%. Great practice problem, 9.49. Let's see, molarity is the other way we convey concentration. So molarity, capital M, is moles of solute divided by liters of solution. So you definitely need to know these two equations for the final. Write them on your note card. We can also use molarity as a conversion factor between, guess what, moles and liters, okay? Between moles and volume. Liters is a unit of volume. So there was a diagram that was really important to us when we were using molarity as a conversion factor. Problem 9.59 would be a great practice problem. So if you start out, if you have some chemical reaction, A plus B makes C. And we are given the molarity of A, let's say it's 0.5 molar, and we have 10 milliliters of it, and we know it's going to react with B, and we say how much, what volume of C, if we had it at a molarity of 0.25 molar, how many milliliters would we get of that concentration of solution of C? Here's the diagram. Okay, you would start out with the volume of substance A, and then you would convert to moles of substance A, and then you would convert to the moles of substance B. And really, I should honestly probably use numbers here because I used A and B in the equation. I don't want you to get confused. We'll just say substance 1 and substance 2. And then you could get the volume of substance 2. Now, how do we do this? It's a three-step problem. Well, the first thing we would do is use molarity of substance 1 to go from volume to moles, because remember, that's what molarity lets us do. We can convert from moles to volume, to liters. So use the molarity given, which here would be 0.5. How do you go from moles of one thing to moles of another? We use a mole ratio. And then lastly, the third step, we would use the molarity of substance 2 to convert from moles back to liters. Now, if you look at this, I'm going to point something out really quick. Erase this line here. If you look at this information given, you have a molarity, you have a volume, you have a molarity, and a volume. A lot of people will try to use this equation right here, M1V1 equals M2V2, to solve for stoichiometry problems like this. And you cannot. Why can you not do that? Because of the mole ratio part right here. You have to use a mole ratio. So make sure if you have a chemical reaction is involved in your problem, then you will have to follow this diagram that we just outlined. Okay, you cannot use, it's not a dilution problem. The problem will tell you, it'll use the word dilution or dilute or something along that line, if it wants you to use M1V1 equals M2V2. All right, last, when you do dilution problems, however, you definitely need to know M1V1 equals M2V2, and you have a stock solution that is more concentrated oftentimes, and you're trying to take a portion of that and dilute it, add some solvent to get it to what we call a working concentration, the concentration you want to use for your experiment or to inject into someone's body, whatever the reason is. So M1V1 equals M2V2 there. You can, as long as your units for your volume match, they're both liters or both milliliters, you'll be fine. Osmosis is the last big topic from Chapter 9 to make sure you are familiar with. So understanding units of osmolarity. Notice I did not put equivalents on here, but osmolarity, okay, which is number of moles of particles. We don't care if you're an ion or a molecule like glucose, but number of moles of particles per liter of solution. Okay, so if we have 1 liter of solution and we have a lot of particles in it, it will have a higher osmolarity than if we had another liter of solution with very few particles. Something with a high osmolarity, I'm going to move this down actually. Hypertonic solutions have higher osmolarity, meaning they have more particles in the solution compared to their neighbor, hypotonic. This is solutions with a lower osmolarity, less particles. And the goal of osmosis is you're trying to create isotonic solutions. So solvent, here in osmosis, the thing that happens is solvent moves across a membrane, semi-permeable, from areas of high osmolarity. Sorry, I have that backwards. They move from areas of low osmolarity to areas of high. Okay, it's not the solute particles that move, it's the solvent. Solvent moves from an area of low particle concentration to an area of high particle concentration in an attempt to dilute it. Okay, that's the way the gradient is set up. So that's kind of it for osmosis. That's it for Chapter 9.